Hello everyone and welcome back to this online NPTEL course on aquatic geochemistry. In our previous lecture, we had been discussing about the rubidium strontium isotope system, and I had discussed how rubidium decays to strontium, and that strontium could be so useful in particular applications for understanding of weathering processes, and for the long term understanding of the global carbon cycle and therefore the climate. In fact, most a significant amount of evidence is found from the strontium isotopes, because it provides solid evidence of weathering related activities, how it has changed over Earth's history. Okay. So, I had shown you this figure that we have been observing a huge variation of strontium isotopes over the past 600 million years, and today particularly I will be talking about a few of the applications that we use of these isotope systems. So, as I have already said that these isotopes we use to infer the tectonic events, and we also use them to infer about the weathering. Okay. So, they are connected, right. If there is a lot of tectonic activities going on, then there will be a lot of weathering because of the enhanced physical weathering. Okay. There can be earthquakes, and can be landslides, there can be a lot of other and high energy events. So, these high energy events will drive more weathering. Okay. So, therefore, if there is more weathering, that means there will be more supply of higher or more radiogenic 87 strontium by 86 strontium from the continents to the land mass. Or if there is a lot of underground volcanic events going on. Okay. If there is subduction going on, a lot of hydrothermal activities are going on. What will that do? Then that will if there is more of hydrothermal event that is happening, then that will release more unradiogenic strontium to the global ocean. So, we will have more pulling down signatures. Okay. So, it will suddenly dip. Why? Because there is more unradiogenic strontium coming from these hydrothermal vents, coming from these submarine volcanoes. So, they will cause this kind of dipping in the radiogenic values. So, it is all linked. The weathering is linked with tectonic events, that is linked with the global climate. So, let us see what particular applications we use strontium isotopes for. So, one of the applications is, of course, we understand how we infer, or we know we get evidences, we gather more evidences to support our tectonic events. Okay. So, tectonic events, when we when we are doing studies that is related to Earth's past history, a lot of evidence is required, and we need evidence from all fields. Okay. Every theory that is put forward, it needs to be backed up by geophysical evidences, geochemical evidences, biological evidences. Okay, all kind of paleo indicators that are there. So, we dig up, we see okay whether this particular theory supports all these evidences or not. And since strontium has such a high residence time in the ocean, it is extremely useful. And the second reason that we use strontium isotopes so much is that it is so high in the continental crust. Its continental signature is very strong. Okay. It is not like it gives distinct signatures to distinct continental land masses. So, that is very useful in understanding these kind of tectonic events and all. So, this is a figure where a plot of, in the x axis we have the time scale in millions of years. As you can see, it has been divided into some of the large like Jurassic, Triassic, starting from cryogenic era, we have divided into all the different eras, and then we in the y axis we have plotted the 87 strontium by 86 strontium isotope ratio, and in the gray bars only some of the most significant tectonic events that resulted in the formation of large igneous provinces has been plotted. So, again this is just as another application. So, we are plotting on the strontium marine isotope record, we are plotting the large igneous provinces record. Okay. So, you can see that over this 700 million years there has been very many significant development of large igneous provinces. What are large igneous provinces for those of you who are not of earth science background? So, large igneous provinces are very particular events wherein huge continental flood basalts are generated. Okay. For instance, we have our Deccan basalts. Okay. So, in India Deccan plateau is a very is a geomorphic kind of landform. It's a very separate kind of landform. So, in India we have this Deccan plateau over here. Okay. So, this Deccan plateau region, this got formed around 65 million years ago. Okay. So, around 65 million years ago, when the Indian plate was moving, okay, there was a huge magma hotspot that was leaking this that was releasing this hot lava. Okay. And these lava, they get with continuous eruptions and all, they form these large flood basalts. So, why do we call them flood basalts? Because they are like thin eruptions. So, they are like a it's like a flood, it's like flood water getting layered by layered by layered. Okay. So, this is going on for a few tens of millions years. Okay. So, in Deccan basalt, if you see, there will be layers of magma that you could be able to date, that got solidified to what we today call the Deccan basalts. Okay. So, such kind of activities wherein huge amount of magma got generated and it made continental scale land masses. Okay, it made continental scale land masses. These are what we called large igneous provinces. Okay. This is what is called large igneous provinces. If you want to look into more details, you can go and check these particular papers, but this is just for us to discuss how we are going to apply the rubidium strontium isotope system information. Okay. Then how do people work? People work with the river data, right? What we can do, right? We cannot go back in time and we cannot do studies from 600 million years ago, 700 million years ago. What are we going to analyze? We are going to analyze only river data. And why river data is so important? Because rivers, they are called basin scale integrators. Okay. That means rivers, they drain through land masses which has which can have a hugely varying geology and hugely varying time scale of formation of those rocks. So, when we are looking at river data, we can have some types of rocks which are extremely old and will have therefore more radiogenic signatures, and comparatively if we have some other types of rocks and which are more younger formation, then we will get that difference from a more younger contribution to a more older contributions. Okay. So, rivers that are flowing through different landscapes, different geology, they give they give integrated signatures. And also in in the strontium cycle that we looked in our previous lecture, rivers they supply the higher 87/86 strontium signatures, that is the more radiogenic. So, more radiogenic values are there. Okay. So, when we are looking at the ocean and we know that okay, rivers are our only source of radiogenic strontium, then of course, the entire community will be very focused on understanding how 87 strontium by 86 strontium is varying in the rivers. So, therefore, this shows the entire world region, and in this donuts you will see how many numbers of rivers has been analyzed from that particular area and how much these rivers totally contribute, okay, from this region. So, 19 rivers, okay, from this region has been analyzed and they form around say around 20% of the discharge that comes from this area. Okay. Rest 80% has still not been done. Okay. So, some of the areas depending on the location has been very well studied. For instance, this area in northern America, some parts of Canada, that has been very well studied, and as you can see this donut, it shows that the 16 rivers that has been studied almost contributes 2/3 of the entire discharge, and therefore, this area is very well quantified and this is the average. So, 0.7172 is the average radiogenic signature from that area. Let us look into another area which is here, which is our India and this particular landmass. So, from here around 23 rivers has been studied and very close to 50% of the discharge has been very well monitored. Okay, and this has been taken in this evaluation of the average value. So, this is the global average value, right. This global average value that somebody is weighing in and finding it to be 0.7113 has come from this entire global data set. Okay, has come from this entire global data set. Okay. So, this is the plot of how it is done. So, we have all these rivers. Okay. Each individual point in this figure is a river. Okay. So, every individual river that you are seeing here is a particular river. Okay. So, from this entire data set, okay, which again has been cropped to 0.74 as it has been mentioned. It has been cropped because these are very small radiogenic rivers and their contribution falls more on this lower side of the total strontium flux. So, their significance in this study becomes a little low. Therefore, they had it has been cropped and all the major rivers has, if you see how do we calculate flux, what is flux? So, flux is the amount of concentration of a particular metal. Okay. So, this metal concentration which will be in something like milligram per liter, okay, or microgram per liter if it is any other element. If strontium is low, it will be measured in microgram, if it is high, it will be reported in milligram per liter. So, this strontium, if you multiply that with the discharge, okay, you multiply that with discharge value. So, 1000 liter, okay, per second. Okay. So, this value, if you take the annual flux, okay, what is the annual discharge? and you multiply that with this microgram per liter, okay, then you will get the total strontium flux in tons per year. So, of course, you have to, it will be a huge number. So, it is generally reported in few tons per year scale. Okay. This strontium that we are multiplying with the discharge, this needs to be very well quantified, whether it is seasonal, whether it is very stable over the seasons, because sometimes the strontium value can have high seasonal differences. Okay. So, such discharge weighted concentrations has been used in this particular figure, and these individual points shows the discharge weighted strontium flux and their strontium isotope signature. Okay. So, for instance, after doing this entire study, we are coming to a conclusion that this is the average, okay, this is the average river signature. Okay, this is the average river signature, that is the cumulative river signature. Okay. So, this is how we do this value that we get 0.7113, or if somebody has any other value, this we are going to fit in all the box models, okay, all the box models for strontium global budget. Okay. So, when we are going to do that global budget calculation, we are going to use these particular values. So, particular applications of strontium isotopes. Okay. First is determination of the bedrock age. As I have said, that continental crust is having high radiogenic signatures, and the more the age the rock is, the signature isotope signature increases. Okay, it becomes more and more radiogenic. Okay. So, from the river data, can we calculate back what is likely the possible bedrock age? So, this has been done for several rivers, and this plot shows the the errors that is involved in determining the average. And since again I repeated that rivers are basin scale integrators. So, they give very nicely the average composition. Okay. They themselves, they will give you the average composition of say the Mediterranean region, or of the Western Europe, okay, or of East Asia. Okay, what is the value? Okay. So, we have such values that has been calculated very strongly from the 87 strontium by 86 strontium data. Okay. And this, in this figure, it shows how the different different land masses, what is the signature from the different land masses are, and this comes from more this is the more unradiogenic value to the average, and this is the highest values that has been observed from the average calculations. Okay. You can look up this review paper for more detailed understanding. So, first we looked into bedrock ages. Now, we are going to understand how some geochemical processes are going to happen. Okay. So, 87 strontium by 86 strontium, okay, will be high in silicate rocks. Okay. It will be high in silicate rocks, but what if I tell you that certain carbonate rocks, okay, certain carbonate rocks also show very high radiogenic 87 by 86 strontium values. Okay. Some regions, particularly in the Himalayas, we have a record of certain types of carbonates from the lower Himalayan stratigraphic series that have extremely high 87 by 86 strontium that can reach up to values of 0.8. So, just imagine we were moving in this 0.7, 1, 2 and all, and now we have rocks and specifically carbonate rocks where we have radiogenic signatures that can reach up to 0.8. So, this became a very point where why suddenly carbonate rocks became so high in radiogenic 87 by 86 strontium, because carbonate rocks, they do not host rubidium, right. They do not host a lot of rubidium such that they will become radiogenic with time. Okay. So, they will have mostly the carbonate rocks when they are formed, they will have the signature of the water body from which it is precipitating. So, these carbonate rocks in the Himalayas, they are mostly deposited in the marine environment. So, they are supposed to be having that signature. So, it was supposed to have something like 0.71 or 0.70, but why should it have a signature something like 0.8? So, after a lot of investigations, Mike Bickle in 1994, he gave this theory that during the thrusting and the metamorphic events that was happening during the Himalayan orogeny, that is during the formation of the Himalayas, at that time during the metamorphic pressure and temperature and all the interactions that was happening in that tectonic event, some of the radiogenic strontium, they got inside the carbonate rocks, okay. They got transferred into the carbonate rocks. So, such changes happening during the metamorphism, which is related to a process based change, okay, which is related to a process based change. It came from this understanding of strontium isotopes, and this is true for particular settings only, okay, because here we are not seeing any radiogenic decay, but we are seeing very specific chemical processes during which metamorphic decarbonation reactions that can transfer more radiogenic strontium into the carbonate rocks. Okay. So, this is one application of strontium isotopes. Again, we have already discussed that strontium isotopes can infer a great deal about the weathering cycle, about how weathering has varied over the earth's history. So, over the earth's history, as we have seen, there has been many ups and down cycles, right. But over the last after 100 million years, as you can see, there is a gradual increase, and this slope after 40 million, around 40 million years ago, I think it has become steeper, right. So, this slope suddenly became much steeper, and this was extremely intriguing for all the geochemists. So, something which was supposedly going like this or maybe increasing a little, suddenly took a curve like this. Why is it moving so high? So, for the last 40 million years ago, strontium in the ocean is becoming steadily more radiogenic. So, why is this happening? Why is this phenomenon we are seeing? So, among all the different type of theories that geochemists have proposed, the one standing theory that has been proven and backed with a lot of other evidences is that the weathering of the Himalayan Himalayan mountains, and specifically due to the large rivers that drain this Himalayan region, they can become important contributors to the marine budget. Okay. Now, here let me go back to this particular slide and just show you two things. So, here you see that this is the strontium flux that is coming in. Okay. And I told you when we are calculating flux, there are two things that is important. One is the strontium concentration and the other is the discharge value. Okay. Now, as you know that the highest discharge, the river that has the highest discharge is the Amazon river, right. It is the Amazon river. So, the Amazon river should also have the highest flux because its discharge is many times higher than the next second highest river. Okay. So, it is even higher than the second highest river. So, Amazon river is this particular river which is extremely high discharge. It has the highest flux here, but this does not have very radiogenic contribution, right. As you can see, its contribution is around 0.711. Okay. So, its value is very close to the average river composition, which is like 0.7113, right. So, when we have to give evidence for why the global ocean is moving towards more radiogenic contribution, then we have to look for rivers which has more radiogenic signatures. And in this particular regard, we have two particular rivers that we see have high discharge as well as more radiogenic, and this particular river is no other than our Ganga river. Okay. This particular river has high strontium flux as well as has high radiogenic signature, and not only Ganga, the Brahmaputra, the Brahmaputra river as well has significantly high radiogenic signature, and of course, it is one of the large rivers as well. So, it has high strontium flux as well. So, there was a very strong theory that these rivers which is draining from the Himalayas, they will be able to drive this high radiogenic curve that we are seeing in the marine record because of their high radiogenic signature and their high discharge values. Okay. And as we know that we we have seen a lot of monsoon fluctuations, the discharge can have also have a lot of history. So, all this theories we have there has been many geochemists who have studied these particular rivers, the Ganga and the Brahmaputra specifically, to understand why or whether it is possible for the Ganga Brahmaputra discharge to drive this marine isotope record more towards a radiogenic direction. And people who have studied among them, there has already been a lot of debate of whether it has been the silicate rocks that has caused higher contribution of radiogenic strontium, or whether it is the carbonate rocks, or what is it being controlled. If it is getting more radiogenic, does that mean that the silicate weathering rate has increased over the past millennia, or has it been like this for the several millennia ahead, or how it has varied with time. So, finding about the silicate weathering rate from the 87 by 86 strontium value has been again a great application of these isotope systems, that is how silicate weathering rate has changed over time. And why is that silicate weathering rate important? Because silicate weathering consumes carbon as compared to carbonate weathering. Carbonate weathering does not consume any carbon dioxide from the atmosphere, but silicate weathering rate will show us how the carbon in the atmosphere has varied and therefore help us indicate about the global climate. So, understanding whether it is silicate weathering or whether it is carbonate weathering is extremely important. So, many times we are going to use this differentiation of silicate versus carbonate. Okay. It is very common in all the studies that is aimed at understanding these weathering rates and how it has varied in the past. Okay. So, often we are going to use these kind of plots, okay, where we have the elemental ratio or the metal ratio of calcium by sodium, and in the other axis we are plotting silicate or silica by sodium. Okay. So, this if it is moving high shows more and more silicate contribution, and this if it is moving high it is showing more of carbonate contribution. Okay. So, if it is moving high with the same carbonate as well as silicate, then we have a particular rock type that is rich in both carbonate and silicate, that is more granitic contribution, more coming from the plagioclase feldspath or the calcium rich feldspars and all. So, that we have to be very careful of what is the data that is showing us. Okay. Now, this plot shows silica by sodium ratio and calcium by sodium ratio, and in this plot the color shows the radiogenic signature. The color shows the radiogenic signature. So, as you can see that this dissolved load shows that there is a strong correlation of the silica by sodium by calcium by sodium, and this is very expected given that silicate weathering also releases a lot of calcium and all. Okay. So, from all the feldspars and all lot of calcium is also released. Okay. So, weathering is causing this good correlation, but at certain times silicate weathering rates are high, and during these particular high silicate contributions we are seeing very high radiogenic signatures. So, red means a value of 0.7636 varying to 0.7571. Okay. So, when suddenly the silicate contribution becomes very high, we are also getting very high radiogenic signature. Okay. So, this is from the Ganga. Okay. So, this plot, okay, if we are seeing it in terms of calcium by sodium by magnesium by sodium. Why we are plotting calcium by magnesium? Because in this kind of plot we can differentiate well within the different rock types. So, this is the carbonate signature, this is the carbonate end member. Okay. What do I mean by that? So, this particular value is the value of a river that has flown through monolithologic carbonate rocks. Okay. That means there is not a lot of mixed rocks. Okay. It is having similar rock which is all carbonates, and that is the particular signature of that river. Similarly, this is again the value of river that has mostly flown through a basaltic terrain, only and only through a basaltic terrain. So, this is the basaltic signature, this is another river from the granite, this is what evaporite. Okay, evaporite is another different kind of rock type, okay, that kind of signature. So, carbonates having very high calcium and magnesium as compared to evaporite. Evaporites are formed mostly from the evaporation of salt water, that is basically ocean water, and they will form all the salts which will over time get solidified and form a rock. So, those rocks are called evaporite rock types. Okay. So, we have evaporites, we have granite, we have basalt, we have carbonate, which are the most major rock types. And here the data of Ganga has been plotted with some differentiation. So, differentiation between temporal. So, there is monsoon and non-monsoon. As you can see, the monsoon ones are shifted more towards the carbonates, the non-monsoon ones are a little placed downwards. So, there is a mixing happening between a granite and a carbonate and maybe a little bit of basalt. So, if I draw a mixing line, we can see that there will be a granite end member and maybe another carbonate end member. Okay. Now, plus signs, as you will see, is the major data here. This plus signs is the Ganga from the Himalayan region. Okay. The Ganga from the headwater region, that is when it is flowing through the Himalayas. And as you can see here, that it shows that the carbonate that it is flowing through can have very high values. Okay. It is having very high calcium by sodium by magnesium by sodium values. Okay. So, our carbonate end member can be actually sitting here. Okay. This carbonate end member can be actually sitting here, and along with that some other values has also been plotted, such as hot springs, cold springs and rain values. Okay. It shows how the river values are changing with season and with the spatial scale. So, this is Ganga in Bangladesh. This is the data of Ganga at a particular place called Farakka, which is in West Bengal. This Farakka is the final final place after which Ganga enters Bangladesh. So, this is that data, and as I said, this plus sign, this data is from the headwater region. Okay. So, such understanding of spatial temporal variations helps us understand which region gets controlled by what kind of weathering, how it is modulated downstream. In downstream, if it is shifting, what is it is shifting, whether it is getting the shift is from weathering rates, or the shift is more related to the type of rocks that it is draining, and therefore, we try to find out if the radiogenic signature, with the radiogenic signature, if we can see some pulses, and if we can use this kind of information to understand how it has varied over the past. Okay. So, with this I will stop in today's lecture, and in the next lecture I will start another new radioactive isotope system, which will be the samarium neodymium isotope system. Thank you.